stop me and we'll quit so that you could put your minds to other things. So we'll try to wrap things up in a timely or perhaps more than timely fashion today. But sometimes I get a little bit lost in time wise, and so you might need to yell at me just a little bit, but hopefully you won't have to do too much of that. So as we get started, let me first of all inquire about whether there are any questions, comments, additions, whatever it might be that any of you might have. If it has to do with your upcoming exams outside of this class, I probably can't help you. I probably don't know. Okay, well, you know, if things do arise question-wise along the way, make sure to jump in, and I'll do what I can to address them now or find an answer for you at a later time. It's just been a week now that's expired since the Nobel Prizes were announced in the various scientific disciplines, including chemistry. And as we talked about a little bit yesterday, this is National Chemistry Week right now, as well as National Pharmacy Week. So I thought I've wanted to do a little bit with the chemistry prize, since it's so vital towards our interests in pharmacy, and figured if I don't say a little bit about it now, I'll probably forget and lose track of things, and this will all just sort of disappear into the background. So I thought we'd spend just a little time with that today. So I brought in a recent copy of a publication called Genetic Engineering and Biotechnology News. It's a lot like Chemical and Engineering News from American Chemical Society. And the lead article in here, which really isn't the one that I want to look at, but is very interesting, is entitled indeed Drug Discovery. And it talks about various aspects of drug discovery associated with robotics and artificial intelligence. So it's a pretty cool article. But the one that's relevant as far as the Nobel Prize this year is concerned, the article is entitled CRISPR Startups Explore New Twists. And goes on to subtitle, it says CRISPR startups give genome editing several new twists. And then it sort of further introduces things by saying base editors, exonucleases, and other refinements enable advances in pathogen recognition, antibacterial development, genetic medicine, xenotransplantation, and agriculture, which is sort of a wide swath of interesting and useful things. So I'm going to, it's a pretty long article, and we don't want to spend all day on it by any means, but let me just read a little bit of the introductory aspects to this, and then a little commentary I'll make after that, because there's some interesting sort of political as well as scientific aspects of what's going on in this particular issue. And not unlike other things that we were talking about, where there's this tremendously dynamic interface between the scientific world and other aspects of our world, including government, regulatory affairs, and politics. And by the way, I think people are all aware, but probably too busy to worry about it too much. I'm not sure I'm going to watch myself, but the final presidential debate is on this evening. I have a hard time with these debates. I'm not very fond of them. So I may just rely upon Stephen Colbert or somebody like that to tell me what happened in the debate tonight. But anyway, early this evening, I'm not sure if it's 6 or 7 o'clock this evening, the final presidential debate will be on. Okay, so back to this article on CRISPR startups. It says, to begin with, just 7 years ago, the Broad Institute's Feng Zhang and Harvard geneticist George Church separately demonstrated that in human cell cultures, genome editing could be performed using a CRISPR system. CRISPR, and I always forget what it stands for, but it's going to tell us right now. CRISPR, which stands for Clustered Regularly Interspaced Short Palindromic Repeats. No wonder they use the acronym. Wow. First came to light as part of a naturally occurring defense system in bacteria. And of course, and I'll just jump out of this just for a second. That's what the Nobel Prize in Chemistry was awarded for a little week ago. Jennifer Doudna of the University of California, Berkeley, and a European associate of hers were awarded the Nobel Prize. Note, just to give a little lead in on the political side of things, that there is no mention of Doudna and the other Nobel Prize winner in this particular article. It's other people that are discussed. Okay, so CRISPR DNA in bacteria include repetitive elements, spacer elements, the latter of which encode RNA molecules that complex with the CRISPR-associated or CAS nuclease and guide it to viral targets. That is, viruses that possess genetic material complementary to guide RNA. After Zhang and Church showed that CRISPR-Cas9, one of the crude adaptive immune systems found in bacteria, had potential as a genomic engineering tool, many developers followed their lead. Early CRISPR startups, and so there's this sort of commercial aspect of this too, and therein lies the rub in terms of the controversies here. Early CRISPR startups, these companies such as Editas Medicine, CRISPR Therapeutics, and Intellia Therapeutics went public and have since prospered. And now a new crop of startups is showing that there's still plenty of room for innovation. Each of the new CRISPR startups features a unique twist on the original CRISPR formula. Examples of different CRISPR new techniques include exotic enzymes and novel sophisticated editing mechanisms. In this article, we present 5 CRISPR startups. Their application range from making vegetables taste better to diagnosing COVID-19 in low resource setups. So that's quite a spread. So those 5 startups are then the discussion. And then I'm not going to go into those. If anybody's interested in this and has time, let me know and I'll get the information to you. But let me spend just a few more minutes on this controversy that exists. There is this huge lawsuit going on between the University of California, which is Doudna's institution, and Harvard and the Broad Institute, which, if I'm not mistaken, is a affiliate of the Massachusetts Institute of Technology, MIT. The latter of those, all of which are there in Cambridge, Boston area of Massachusetts in the United States. So if I get this correctly, the Broad Institute in Massachusetts and then the University of California, Berkeley in California are both laying claim to sort of the patent rights to the CRISPR technology. And this is no trivial matter. The estimates for what's at stake here are in the range of many, many millions, perhaps even billions of dollars, because of the generality of the CRISPR technique and its power in so many different things, as this little article was pointing out. Don't expect an early answer on this. I think this could take years to wind its way through the judicial system and see how it all plays out. But you can bet the principals in the litigation, the Broad Institute and the University of California, are anxiously awaiting the ultimate outcome of this litigation. Both places have very large patent funds in which they disperse portions of that to their researchers, including graduate students in those particular areas. So there's quite an argument going on, and again the Nobel people in Scandinavia did not mention the people from the Broad Institute, and this particular article in Genetic and Engineering News did not mention the people from Harvard. There's not only um, a lot going on here commercially and of course scientifically, but a lot of hurt feelings and potential hurt feelings associated with the claims of priority as far as the discovery is concerned. So it's definitely something to put on your let's keep track of this list as it unfolds over the next few years. And again, I don't think it's going to unfold rapidly. And there may be sort of subparts of it that'll unfold at slightly different times as we progress through this. So anyway, a little bit of controversy associated with science and this year's Nobel Prize. Anybody have any thoughts, questions, input in this particular area? You can bet that at the very least scientifically, these matters are going to make a difference to all of us in upcoming years. All right. Well, any questions so far on sympathetic pharmacology? Okay. Well, if you're feeling tense, transport yourself and your mind to the maroon bells. See if that can soften the psychological load a little bit. Or to the Central Florida location of this manatee. I can't remember where this particular picture of the owl was taken from, but that's so neat. You can bet that Tara is not worrying about exams right now, but rather about dreams. And hopefully this is not the state you are in. Fight, flight, or fright. Perhaps some minor variation of that. We try to keep the stress at a manageable level. So as we talked about the sympathetic system the last few days, we revisited our earlier discussion of the autonomic square, which entails components of both the parasympathetic and sympathetic side of things. If you recall, we're talking about agonists in both categories and antagonists in both categories. And our emphasis in the last few days has been on the agonistic side of the sympathetic system, starting with direct acting agents that are in intimate association with adrenergic receptors, both alpha and beta, to initiate at least some of the consequences of these agents. Again, we talked about sort of promiscuity and the fact that many of these agents interact with receptors and targets other than adrenergic ones. And I'll say a little bit more about that today. But the thrust of the discussion clearly has to do with alpha and beta adrenergic agonists like epinephrine, which is fully represented across the alpha beta spectrum, or as we'll remind ourselves again in a couple of minutes, norepinephrine, which has both alpha and beta characteristics, but has the full alpha load, but a weakened beta load compared to epinephrine. And I encouraged you to compare this direct acting sympathomimetic slide with the direct acting parasympathetic or muscarinic slide that we encountered before, and saw that the two areas are just pretty much opposite from each other, with some additional caveats, particularly that the stimulatory metabolic component is pretty much a characteristic only of the sympathetic side and not the parasympathetic. But both systems have dramatic effects in the lungs, of which there's a relaxation of smooth muscle on the sympathetic side, which allows for more convenient and supple breathing, which is necessary under fight or flight conditions. And then the opposite of that, bronchoconstrictor effect over on the parasympathetic side. We also contrasted the concept of indirect acting agents back in the parasympathetic side, which basically referred to acetylcholinesterase inhibitors, which both Katie and I have talked about, as opposed to release mechanisms over on the sympathetic side, where agents like norepinephrine, ephedrine, and amphetamine mostly show their effects by increasing release of norepinephrine, and then the norepinephrine itself being the primary effect at adrenergic receptors. So there's alpha beta discrimination in the sympathetic pharmacology. And we gave another example of a classical, pretty much all alpha agent in phenylephrine on the sympathetic alpha side, and then isoproterenol on the sympathetic beta side. We talked just a little bit about some either lack thereof or selectivity that does exist. And an example of that is albuterol, which is relatively selective for beta-2 adrenergic receptors. So going back to isoproterenol, which is all beta but doesn't discriminate between beta subtypes, there's an important distinction in the pharmacology between albuterol and isoproterenol. And once again, thinking pragmatically and strategically as far as exams are concerned, all the names that we've encountered here over these couple of slides: epinephrine, norepinephrine, phenylephrine, ephedrine, amphetamine, isoproterenol, and albuterol would be areas that would be prime subjects for examination on the next exam a couple of weeks down the line. So, for example, if we led with a question like, let's just take phenylephrine as an example, you would see that drug name, classify it. Hopefully you would classify it as an indirect, classify it as an all alpha agent, and then characteristics of that, which would include, for example, extreme vasoconstriction, would be components of that. So you need to do that sort of classification exercise as far as the drugs are concerned, as far as their actions are concerned. And if you do that with respect to these various areas that we're talking about here, you should be at or near 100% level on the autonomic questions on the upcoming exam. The complications that occur as we move on from one examination area to another in pharmacology, of course, is that we keep adding new classifications. And so there's more drug names that arise. And as more drug names arise in those particular kind of classifications, then we have more effects that we have to account for underneath those classification categories. So using the old forest and the trees analogy, the forest continues to get thicker and thicker and thicker with trees, which is basically drug categories and drug names and drug effects. And it gets to be a bit of a challenge in differentiating between those various areas. So in that context, the slides that I've put together here, as you can tell, in the autonomic nervous system, both parasympathetic and sympathetic, are very minimalist in their nature. It's sort of cutting to the very bone of these subjects. And there's, much more that goes beyond this level if we were to expand this out, which of course in the reading, Goodman and Gilman especially, but also in Katzung, occurs as many sophistications in these areas are written about in those appropriate sections of the reading. But from a pragmatic sense right now, as far as exams are concerned, I wouldn't limit my studying to these slides, but I would heavily emphasize these slides because the drug names, the drug categories, and the effects that are listed on these slides are the very ones which are most likely to arise in the examination. So rest assured that by having a good handle on the information in the slides, as minimal as it might be, will nevertheless be maximal to you in terms of forging the pragmatic application of getting a good score on the exam, which I know is an important matter to all of you, and reasonably so. Now, our learning these things, of course, goes well beyond exams, and has carryover after the exam, and in terms of practice. And I'm always hopeful that the minimalist slides allow us to carry over some of this information into the future. To me, just take my aging brain as an example. When I look at one of these areas in great detail, I have a hard time in keeping track of that over a longer period of time. But the essence of these topics, which hopefully arises on these slides, is something that I can take with me from one day to another, from one week to another, from one year to another, to some degree. So if you have questions about sort of the minimalist nature of these particular autonomic slides, that's just a little bit of rationale that I thought I should provide you, giving you some insight into the pragmatics of these areas, both in a temporal sense now and for later times. So as we were wrapping up yesterday, we were making the transition from the sympathetic agonist side to the sympathetic antagonist side. And as you already know, perhaps, or guess, if you don't know already, the alpha and beta aspects are represented on the antagonistic side, just as they are on the agonistic side, which then allows us to complete our autonomic square, where at each of the four corners we have the two sets of antagonists and the two sets of agonists represented. For many years in autonomic pharmacology, there was some level of selectivity and some level of non-selectivity also. So alpha versus beta selectivity on the sympathetic blockers slide has been known to some degree or another for quite some time. Matter of fact, for better than half a century. So, for example, if we were to pick up an earlier copy of Goodman and Gilman, let's go to one, for example, out of the late 1960s or early 1970s, we would see information there that allowed us to discriminate between alpha and beta receptors. So, for example, phentolamine is a classical sympathetic blocker, which has almost completely alpha characteristics. It has very little impact upon beta receptors. And if we move down a few lines, propranolol, same sort of thing, but on the other side of it, propranolol has, in an autonomic sense now, fairly great selectivity towards beta and very little actions over at alpha. Now, notice I qualified that selectivity of propranolol a little bit because it turns out that propranolol especially has impacts on some targets outside the autonomic system, outside the adrenergic system, which complicates its pharmacology, but also makes it a very, very interesting sort of compound. So we'll just sort of stick to the autonomics first, and then I'll make a little referral to beyond autonomics after that. Notice that now, if we move forward in time from the 1960s or 70s, where we could have nice alpha beta distinction, but not much distinction inside alpha or inside beta, to the present day, we see that further aspects of selectivity have occurred over recent decades, and so, for example, just an example of that would be we have now a series of relatively alpha 1 selective inhibitors, and an example is given there. These breakthroughs in selectivity on the blocker antagonistic side were as important as the breakthroughs in selectivity that we saw along these lines over on the alpha beta agonist side. So if we look down on beta 1 selectivity moving to the beta side, we see atenolol, for example, which is often considered to be the prototype beta 1 selective agonist, antagonist. So let me just give you a hint of why this is a big deal. We talked about, if we just, let me just go back slightly to albuterol and talked about how it was really neat that albuterol is more selective for beta 2 receptors than other beta receptors, and therefore you get a reasonably selective agonistic effect in the lungs with albuterol, because the lung adrenergic representation is highly beta 2. So you get sort of the other thing going on here with respect to beta blockers. You may have reasons for using a beta agent because of some heart-related things, which are typically beta 1, but you don't want to block what's going on in the lungs, because if you do, then you're going to create a problem with that would be the opposite of what we saw back with albuterol. So you'll hear a lot more about this next semester when cardiac pharmacology is discussed in great detail. But the ability of an agent like atenolol to be able to produce some level of antagonism in the heart, but basically staying away from the lungs, is a big deal. It's a big deal in terms of safety and efficacy. And it's also important to point out that we put sort of quotes around selective for a reason. And that is, although these agents tend to be, quite differentiating between these types of receptors, rarely, if ever, are they absolutely purely selective. And therefore, if one is, for example, using an alpha, or a beta 1 selective agent like atenolol, we have to remember that there may still be some small aspect of other beta activity left in the structural information provided by those drugs. So it's often, or perhaps always, important to be very careful about how far we take the idea of selectivity. So sympathetic blockers. Now, there's another category here, which is often labeled as the sympatholytic category, or the sort of breaking the sympathetic system category. Many of these agents, although not all of them, are older agents that have been in use in practice for many, many decades, or in some cases in cultural medicine long before the scientific era. And reserpine, which you've heard about before, I may have referred to it in introduction, and Katie talked about it in her lectures. It's a good example of an agent that's been around for beyond the scientific era. So if you recall, it's a natural product from Rauwolfia, which is a plant indigenous to the subcontinent of India. And one of the active components of Rauwolfia is reserpine, and it's Rauwolfia in the crude form has been utilized for a very significant amount of time, hundreds, if not thousands of years. So that's sort of where old comes from. Reserpine is a depleter of biogenic amines, and Katie did wonderful coverage on the various biogenic amines last week, and it's rather efficacious in that regard. But notice it doesn't really discriminate much between norepinephrine, serotonin, histamine, etc., but rather depletes all of those. Therefore, it's very nonspecific in its actions and is a relatively harsh drug in that particular context. I'll give a little bit more background on reserpine in some upcoming lectures on degenerative diseases of the nervous system. But for now, I would just recognize as reserpine as a sympatholytic, that it's a biogenic amine depleter, and because of that, it's powerful and relatively non-selective in its actions. Now, there's one other sympatholytic that I want to mention in this particular regard, which does not appear on this slide, but it's known as guanethidine, and its pharmacology is very similar to that of reserpine. There's one distinct difference, however, between guanethidine and reserpine. Reserpine is not charged and therefore is relatively widely distributed systemically. Guanethidine carries a formal positive charge, so it's cationic and therefore does not penetrate the blood-brain barrier. And so, whereas reserpine gives both central and peripheral effects, guanethidine pretty much only gives peripheral effects because it can't get into the brain. And that's an important distinction to make. And so there's a little differentiation in terms of spatial selectivity between reserpine and guanethidine. Now, finally, I want to mention clonidine, which is a much newer agent and still very important in terms of clinical medicine in the year 2020. If we look back on things in a classical sense, you might even see in textbooks clonidine listed as an antagonist. So you might sort of see it sort of listed under sympathetic blockers. It's interesting to note that in 2020, you no longer see the same classification. You see it listed as an alpha 2 agonist. You go, wow, what is going on there? Well, note from our studies of what's going on at adrenergic synapses that there's a substantial representation of alpha 2 receptors presynaptically, and that they are autoreceptors. And so an agonist binding to those presynaptic receptors down-regulates the presynaptic side, which of course, down-regulates the postsynaptic side too, because not as much neurotransmitter is being released. So in early experiments, they were not able to differentiate between that presynaptic and postsynaptic effect, and all antagonistic effects at that time were basically viewed as postsynaptic. And so it was assumed that the downregulation that was occurring in the sympathetic system was due to blocking alpha receptors postsynaptically. That turns out to not be the case. So from a mechanistic standpoint, the action is presynaptic and agonistic, but autoreceptor oriented, and therefore giving a downregulation of the system. So that's why there's a little differentiation placed here between these sympatholytics and the previous slide where we look at antagonism, but in a more traditional uh, pharmacological sense of interaction at binding sites on alpha and beta receptors, and therefore restricting the ability of agonists to reach those binding sites. So some interesting little mechanistic differentials there. Now, if I can do this, and I'm pretty bad at this, I'm going to switch over to our parasympathetic slide if I can. Slides. See if I can pull this off. Okay, so I'm going to spend a few more minutes here as we wrap up autonomics by referring back to the intro to autonomics parasympathetic system slide. And I don't know if you have that readily available or not, but let me just quickly go through some of the relaxing stuff here in case this lecture has raised your sympathetic tone too much. There's Franny Boy again, showing parasympathetic dominance there. Pretty relaxed there. Eddie's imbibing a little bit of relaxation himself in this slide. Jacob is a growing boy now and just beginning to walk. So there's our autonomic square again. Here's our comparison of the direct-acting parasympathomimetics with the direct-acting sympathomimetics that we just looked at. And indirect, of course, here are the cholinesterase inhibitors. The dramatic stuff that we now know about active sites of cholinesterase. Ton of research done in this area over many decades. And peripheral nervous system parasympathetic antagonists. Atropine, of course, has central effects too, but the specific effects of great interest in terms of direct receptor blockage are referable to the peripheral system. So atropine is a classical muscarinic blocker, and is such an important agent. Perhaps on the parasympathetic side, perhaps there's nothing more important than atropine and its analogs, whether we're talking about antagonism or agonism on the parasympathetic side. Atropine is a standout agent. So likely to see more questions coming on exams relative to atropine. So the place I wanted to spend just a little bit more time is here on nicotinic receptors, because almost all of our emphasis so far has been with muscarinic cholinergic receptors and alpha and beta adrenergic receptors. But I don't want to completely slight the nicotinic side of it. And recall that in a general differentiation standpoint, nicotinic receptors come in two flavors, the N sub M or neuronal, or the N sub M, and muscular nicotinic receptors. And I'll say more about N sub M in a minute, but right now I want to focus upon N sub N because it's the one that's relevant as far as autonomic pharmacology is concerned. Recall that all autonomic ganglia are nicotinic, and so we don't differentiate physiologically or pharmacologically at the ganglion level because we can't really, because the receptors on both the parasympathetic and sympathetic sides at the ganglia are all N sub N. And of course, there are also CNS effects of N sub N blockers that can make it into the brain. Some can. Hexamethonium is an example of a ganglionic blocker. In other words, an N sub N antagonist that is charged. In fact, it's double charged. So it really can't make it into the central nervous system. So you're going to have pretty much peripheral autonomic effects with hexamethonium. Now, the non-specificity is a big deal because, rarely do we want to either completely block all autonomic systems, sympathetic and parasympathetic, or activate all autonomic systems. We want to do one side or the other, parasympathetic or sympathetic. And so that's why basically these agents are of such little import in a practical pharmacological sense, because they're interacting at both the sympathetic and the parasympathetic sides. That non-specificity renders them almost, but not completely, low in importance from a pharmacological standpoint. Now, in some very, very rare instances, severe nervous system damage in which like the entire autonomic nervous system regulatory pathway is thrown off and all autonomic things are occurring at the same time, a ganglionic blocker might be useful to try to tamp that down. That's an extremely rare, unusual circumstance, however. And so compared to the more purely parasympathetic or purely sympathetic side of things, the ganglionic sense of things is not too important. That's why I left it for last. So I'm just going to say real quickly here something about the N sub M or muscular blockers. That M is skeletal muscle. It's not smooth muscle. So we're outside the autonomic nervous system now. We're into the skeletal neuromuscular junction. It's not autonomic. It's endued with N sub M nicotinic muscular receptors. It's a classic area, however, because the natural product curare and its synthetic analogs now are blockers at N sub M receptors. And therefore, this was important stuff, and Katie mentioned it as important when she was covering general anesthesia, because often neuromuscular blockers of this type are used as adjuncts to surgical procedures. So it's almost a category that we could put in under the anesthetic agents, which I believe Katie did. It's interesting to know, and I'm going to stop here because I know we're running out of time, that there are two different subtypes of neuromuscular blockers. One, which are classical blockers like curare, which interfere at the N sub M receptor by interacting directly with the receptor and blocking the entry of agonists like acetylcholine in a classical pharmacological sense. Decamethonium, which sounds a lot like hexamethonium over on the ganglionic side, and indeed they are very similar to each other, just separated by 4 carbons greater in decamethonium. These are almost super agonists. They bind to the neuromuscular junction like curare does, but rather than silently blocking it, they actually overactivate or depolarize the neuromuscular junction, and that basically sticks the neuromuscular junction in the depolarizing mode, and you can't cycle back and forth between no activation and depolarization, which ultimately produces a block. In the long range sense, the blocks classically or depolarizing look a lot the same. It's just that mechanistically they're different. So I'm going to quit so that you can put your minds to other things. If you have questions about these last nicotinic topics that we covered fairly rapidly, you're sort of more than welcome to ask those next time or by other means. So best wishes to everyone. If anybody has any questions, I'll linger here for a while, but otherwise we're done. And we'll move into degenerative disorders pharmacology next Tuesday at 11 o'clock. Best wishes, everybody.